Oh, anyway, so we're trying to prove the horseshoe lemma about the existence of this resolution of the middle term if we're given two projective resolutions of the left and right terms. So these augmentation maps for the resolutions epsilon prime and epsilon double prime are given, and I'm saying that immediately I can construct the augmentation map for the middle term, the epsilon. Right, so to do this, I need to define this epsilon on both components. So on this component, it's kind of already given, right? Just take this composition. And on the second component, well, we have a map. This thing is projective, so we have a map to the A double prime, so it can be lifted to the A. And then we just take the sum of this map. That's the epsilon. Now this maps has some kernels. Let me write this kernel of the epsilon prime. Here we have kernel of the epsilon. And we have finally the kernel of the epsilon double prime. So of course, by construction, epsilon prime and epsilon double prime are supposed to be epimorphisms. So hence, there is no co-kernel here, no, zero co-kernel here and zero co-kernel here. So if you apply the snake lemma, the snake lemma tell us that actually, well, they actually give us two observations. It's on the blackboard. This is it. Well, I have short exact sequence with three terms. I assume that I have projective resolutions for the first term, A prime, projective resolution for the second term, A double prime. And I'm trying to construct a specific resolution for the middle term such that Pn for the middle term is the sum of the Pn prime and Pn double prime. So I'm trying to construct the differential, and I know all the modules in this resolution already. So for this, I look at this diagram. I apply the snake lemma. So the snake lemma, first of all, tells me, if I look at the co-kernel part, that the co-kernel of epsilon is 0. So epsilon is an epimorphism. And then the second part, since here for the co-kernel it will be 0, it will be something. This is 0, so this something, again, has to be 0. So it's an epimorphism. And the second part is that we have the short exact sequences of the kernels. So kind of going from the augmentation map to the kernel, the augmentation gap map is kind of going to the next step in the resolution, because for these things, I can take the cover by the P1 prime, P2, well, just P1 prime, P1, P1 double prime. So this finishes the base of the induction, and to do the induction step is more or less the same argument. I assume that I have short exact sequence for the kernels that I obtained on the previous step. So here I have Pn, Pn prime, Pn double prime. So these things are by construction epimorphisms. So then again, as before, take Pn prime, Pn double prime sum, and I just do the same thing. I define the map in the same way. So on this component it is given. On the second component I use the lifting property and apply the snake lemma, and again see that this is a surjective map. Well, categorically speaking, epimorphism. So essentially that's the proof. And we need this lemma to prove the following. I think this is the most important property about the derived functors. Yeah, so notice that I prove this for the projective resolutions. Of course, you can use exactly the same proof to prove the dual statement for the injective resolutions. There are no new ideas in that proof. So in the theorem, I have short exact sequence. So A prime, A double prime is a short exact sequence. I have F, which is a right exact functor. So then, there is a long exact sequence of the derived functors. So I have lnf applied to the A, left derived functor with the index n applied to the A prime, then to the A, and then to the A double prime. Then there is a connecting homomorphism, which gives me a map to the Ln minus 1 Fa. And I just continue. So you can see that on the right, eventually you get L0, which is because the F is right adjoint just F, so it ends after n steps. But on the left, potentially it can go to the infinity. So this is the first claim of the theorem, and the second claim is the following. This long exact sequence is natural. So moreover, the long exact sequence is natural. And it means the following. If you have two short exact sequences and a map between them, so one short exact sequence is A, the second exact sequence is B.
Я даже не поняла, откуда, собственно, взялся
Oh, I explained this, I think, at least 3 times. So if I want to define map epsilon on this sum, I need to define this on each component. So on the first component, it is given. This is just this composition. On the second component, well, I have this map, right? And this P0 double prime is projective, so there is a lift to the A. So I take this as the map on the second component. So the map epsilon is the sum of these two maps. Yeah, so if we have two short exact sequences and the map between them, then we have, of course, the long exact sequence for the first short exact sequence. So the same as before. And the same long exact sequence for the second short exact sequence. And of course the naturality condition is that we have the maps between those exact sequences and every square is commutative. So there's such commutative ladder, infinite to the left. So of course, since we already know that the right functors are functors, so the commutativity of all these two squares is trivial. The non-trivial observation is that this square is commutative. So that's the general statement. Unfortunately, the proof of this statement is not short. We need to do some computations. Oh, more or less for the second part, for the neutrality. The first part is easy. Well, let me fix a projective resolution for the A prime and the second projective resolution for the A double prime. Well, then, by the previous lemma, I'll get the projective resolution for the A. So then I can observe the following, that in the middle, say Pn prime, then in the middle I have Pn prime plus Pn double prime, and this is mapped to the Pn double prime. So on the level n, I'll get this thing. So then I can, if I apply functor f to this, using that f is additive, I'll get this short exact sequence. So I want to ask you, is it clear that this sequence is exact? Notice that f is only exact on the right, it's not an exact functor. So since this thing is a split exact, actually this is still split exact. So in particular this is exact. So then we'll get a short exact sequence of complexes okay. Well, since f is a functor, this is definitely a short exact sequence. It is exact on each n. Now the next question, is it true that this short exact sequence of complexes is splitting? Well, the answer is no. That is because, well, you have these splittings here for each individual, and you have a splitting. So on each level, this splits. But the splitting, it doesn't give you a map in the category of complexes. So don't commute with the differentials. So it's true that this is short exact sequence of complexes. It's not true that this thing splits. So now we just apply the result we proved a week ago. Whenever you have a short exact sequence of complexes, you get a long exact sequence of homology, and that's exactly the statement of the theorem. So we proved the first part. So we need to show that moreover part is also true. And this is where we need to do some computations. So let me assume that I also fix the resolutions for the second exact sequence. So I have Q with the prime, that's the resolution of the B prime. I have Q with the double prime, that's the resolution of the B double prime. And again, by the horseshoe lemma, I can produce resolution Q for the middle term B. So then I'll get the following situation. I have short exact sequence of complexes which are projective resolutions of the first short exact sequence, then short exact sequence of complexes which are resolutions for the second short exact sequence. Now I know by the lifting to the resolutions that this map little f with the prime, I can lift to the resolutions. And this lift is unique up to homotopy. I can do the same for the f double prime, right? And of course I can do the same for the map in the middle. So this gives me this diagram. So the question is it true that this is a commutative diagram in the category of complexes? Essentially, this is the biggest problem, because no, this is not true, because this is just a lift, this is just a lift, and this is just another lift. Of course, when I'm saying that this is a map in the category of complexes, I need to say that this square is commutative, this square is commutative. But if I just take, suppose this lift is fixed and this lift is fixed, if I just take any lift for the f, I cannot claim that these two squares are commutative. So I need to say that the two squares are commutative, or in other words, that I have an invariant kind of subcomplex. So in other words, what I need to show is that Fn has a very specific structure. So it has fixed diagonal, and then there is a map gamma n. So if I can find the lift of this form, this is precisely saying that this is a commutative diagram, because this will be an invariant kind of sub-object, and this precisely means that I need to put 0 here. Okay, so essentially what I'm going to show is that there is a lift of f, of little f, which I'm going to call big F of this structure. So the gamma n, for completeness, I'm going to write that this is a map from the Pn double prime to the Qn prime. And the existence of such gamma, again, I'm going to prove by induction. So n equal to 0. This is the base of the induction. Okay, for this I need to draw a diagram. So let me maybe draw a diagram on the next whiteboard. There will be a lot of details on this diagram. Essentially just for convenience to see all the maps that I'm going to use in one diagram. Well, here I have P0 prime direct sum with P0 double prime, the augmentation map epsilon to the A, and then there is Q0 prime plus Q0 double prime. Let's call the augmentation map to the B eta. So here this is map F, and here the map of S is F0. Okay, so just for completeness, let me add the projections. So let me call pi A the map to the A double prime, pi B map to the B double prime, and here the map is F double prime. So this is just the part of the diagram that I just erased. Now I want to introduce something new. So let me consider the embedding of the P0 double prime in this sum. And the composition I'm going to call lambda P. Here I have two projections, two components. So when I consider projection to the Q0 double prime, the map to the B, I'm going again call lambda, but in this case with the index Q. And then there is another projection to the Q0 prime. From this Q0 prime, there is a map eta prime to the beta prime, and from the to the B, and from the B prime to the B, there is the canonical embedding I sub B. So what's the idea behind this diagram? If I want to understand this map, F0, that's a kind of 2 by 2 matrix. So I want to understand individually each component. I can think about this as I consider one component here, and if I, for example, take projection to here and to the first component and to the first component to the second component, this gives me one of the rows in the matrix. Well, if I instead of the second component here, consider the first component. Well, I'll leave this as a little exercise. You won't get anything interesting. It essentially will be the identity for the Fn prime, F0 prime. The interesting part is the second column. Okay. Well, first of all, of course, I have the following, that the eta composition with the F0 is the same as an F composition with epsilon. That's the commutativity of the central square. And if I rewrite this with the map that I introduced, I can say this thing. So this is equivalent to the composition of the F and lambda sub P is the same as the lambda Q F0 double prime plus eta B, sorry, I B eta prime gamma 0. So I just wrote what the second arrow is doing in terms of components. So the second column, not the second column of this matrix, what it's doing in terms of components. Right, so if I the lift of the map. So we have a map here. So these are the corresponding resolutions, and I can lift this map uniquely up to homotopy to these resolutions. So I'm claiming that it's not just any lift, that there is a lift of this specific form. Yes. Well, it's more or less straightforward. If you just replace, for example, zeros here to the n, this will be the general formula for the Fn. This will be mapped from this module to this module. Since this has two components and this has two components, the map is 2 by 2 matrix. well, again, what's a map Fn? That's a map from the Pn prime plus Pn double prime to the Qn prime plus Qn double prime. Right? And then I just write this in terms of the 2x2 matrices. Well, you can see that, for example, Fn prime, that would be a map from the Pn prime to the Qn prime, right? And this map is just Fn prime, so this one. Now, for example, gamma n, I wrote it here, so that is a map from the second component to the first component. So that's the correct position for this gamma. Okay, so back to this large diagram and the computation. So this commutativity condition is more or less the same condition if I just restrict and take this condition and restrict this to the second summand in the P0. Right, just pre-compose with this embedding. Then I can replace this epsilon. So this composition I can replace with the lambda p, what I've done here. So this right-hand side here is the same as the left-hand side here. So maybe it will be better, easier to understand if I just rewrite this. So f epsilon is equal to the eta epsilon. Yeah, and the right-hand side, well, I take this map. So I need to consider this composition, and I can, of course, I can do this by decomposing this into two components. So this will be the first component, just the name lambda q, and the second composition is this composition. Yeah, but at the moment, I don't know that this gamma 0 exists. This kind of what I wish to prove, right? So I want to show that there is gamma 0 such that this formula is true. How we can show that actually such gamma 0 exists? And that would be the base of the induction. Well, I do the following. I consider a map, so I move this lambda q f0 double prime from the right to the left. So they consider a map f lambda p minus f q f0 double prime. And take composition with the map pi sub b. So let me just open the parentheses so that what I'll get, well, if I look at the composition of pi b and f and look at this diagram, I can rewrite this as an f double prime pi a lambda p. So that's the second commutative square. And for the second summand, well, this will be pi sub b lambda q f0 double prime. Don't do anything with this thing. Okay, now next step, this is f double prime. Now the composition of the pi and lambda give me epsilon double prime. And the composition of pi and lambda q give me the eta double prime. So f0 double prime. Now this is 0. Since f0 double prime is the lift of the f double prime. So since this is 0, it means that the map that I consider composition with pi b is 0, it means that this map is not actually a map to the b, but it is a map to the kernel of this thing. So this is a map to the b prime. So hence I can say that there is a map, let's call me temporarily beta, from the p0 double prime to the beta prime, such that this map that I consider f lambda p minus lambda q f0 double prime is in fact the composition of the I beta, IB and beta. Okay, so this is existence of this beta, but then if you just look again at the diagram with the p0 double prime, here is the map beta to the b prime, So this is augmentation eta prime for the B prime. And again, using that the B0 double prime is projective, I can leave this beta and get the map which is gamma 0. So in other words, beta is eta prime gamma 0. Now look at this formula and plug in formula for the beta. We get exactly the right term here. So this proves the existence of the gamma 0. Okay, so induction. So I'm going to first of all say that the commutator of the Fn and the differential is 0, which is of course has to be true if I want a map of complexes. Now let me rewrite this identity in terms of 2 by 2 matrices. For the Dn, I can use the following block form. Okay, maybe I just write the formula and then we discuss this. Okay, so how do I know that for the differential I have the following structure, that I can also put 0 here? No, this is again the horseshoe lemma. Horseshoe lemma implies in particular that the differential has this form by the construction. Because I always constructed this as kind of, in my construction, I always have the sub-complex. And since this is sub-complex, the first column is of this form. So the structure of the differential again follows from the horseshoe lemma. Well, because I have a subcomplex. By construction, when I constructed this resolution for the middle term, the resolution for the first term was a subcomplex in the resolution. I constructed this way. And since this is a subcomplex, it means that I have the first column that has some differential and 0. Well, the second is a quotient complex. It can be a subcomplex. Well, think about vector spaces. We have a vector space and a vector subspace and a complementary vector space. And we have a map from the vector space that has preserved this subspace. What would be the structure of the matrix that preserves such a subspace? It will be always of this form, with something acting on this subspace, 0 here, and then something on the complementary space. The same logic, just basically linear algebra. Well, because we have a subcomplex. Because the second is a quotient complex. Well, we have P. That was subcomplex by construction. Well, from this it follows that this is the differential on the P. Well, I don't know how, but I think it's kind of trivial. Well, we have Pn, right? Here we have P prime n plus Pn double prime on each level. right? And the differential here would be a map from the Pn prime minus 1, Pn minus 1 double prime, right? So it will be described by a 2 by 2 matrix. Well, you have to believe me that this is described by 2 by 2 matrix. You have two objects in the input and the output. So here I'll get Pn minus 1, and this is still a subobject. So we have the induced differential, well, it's a differential on the subcomplex Dn prime, right? What the commutativity of the square is telling me for this matrix? Well, it's telling me that, for example, I have an element here. I consider this as an element in this sum. I apply this differential. So if this will be, and take an element, apply the differential. Well, say let's take a some basic element. If we have a, well, basic is not good. Well, okay, take any element. You take an element, you embed this as an element, this element x, comma 0. When I apply the differential, well, you'll get something here, of course, but then it will be the same thing if you go like this. So this will be, you take the element, apply the differential, and then embed this here. So if you go like this, well, if you go like this, you'll get x. X is mapped to the x, comma 0. This will be matrix with 4 components, x, comma 0, or maybe I write it like this. And here, this will be, this x is mapped to the dn prime x, and this is mapped to the dn x 0. Sure. I assume that I work in the category of modules. If I work in any abelian category, I just use the general theorem that I can embed this as a subcategory. Yeah, but the result is still the same in any abelian category. If you have, say, two objects here, this is a sub-object. If you have a map here, the map on the sum, it will be of the form you have something here and 0 here. Well, okay, so now let's go from this 2 by 2 matrices to the scalar equations. It will be the following equation. So dn prime gamma n plus lambda n fn double prime minus fn prime lambda m minus gamma n minus 1 dn double prime. Okay, so this will be, of course, when I kind of compute this commutator, of course, this term will always be 0. On the diagonal terms will be trivial statements. That will be just statements for the f prime and f double prime. The non-trivial statement will be in this corner. And this is what you get in this corner. So it still has to be 0. Let me introduce for shortness notation. G with the index n is just by definition the last 3 terms in this formula. So gamma with the index n minus 1, dn double prime minus plus f n prime lambda n minus lambda n f n double prime. So if I call this equation star with this notation, I can rewrite star simply by d prime n gamma n is equal to the gn. So this is equivalent to the star up to notation gn. So what I'm trying to do, I'm trying to use the induction, right? So I assume that I already constructed this gammas for the previous steps up to gamma n minus 1. I'm trying to construct gamma with the index n. So that's the equation for the gamma n. That I need to solve this equation. Well, if I, in particular, if I apply dn minus 1 prime to the gn, I need to get 0. If I can show that this thing is 0, then essentially it will be more or less trivial to show that the gamma n exists. It will be more or less the same argument as here, some lifting argument, since everything is projective. So the key step in the proof is actually showing that this thing is 0. Okay, let's try to compute this. Well, first of all, I can do the following. I can apply this d prime with the n minus 1, and the first step I'll get, the first summand I'll get the composition of this dn minus 1 prime with the gamma n minus 1. To simplify this, I can use this equation star, but for the index n minus 1. So this is what I'm going to do in the first step. So this will be f n minus 2 prime lambda n minus 1 minus gamma n minus 2, gamma n minus 2 d double prime n minus 1 minus lambda n minus 1 f double prime n minus 1. Okay, and this is still composition with the d double prime n plus. Well, for the other two terms, at the moment I'm not going to do anything, so plus dn minus 1 prime f n prime lambda n minus dn minus 1 prime lambda n f n double prime. So I hope that there are no mistakes. Okay, so in that computation, well, of course, there are only 4 terms, because here we'll get the composition of the d and d, that will be 0. So actually this cancels immediately. So what the 4 terms that we have in the formula is f n minus 2 with the prime, lambda n minus 1, dn double prime, minus lambda n minus 1 fn double prime dn double prime. Well, I was saying that when I do this computation here, when I apply this differential and try to understand its composition with the gamma n minus 1, I use this formula, but for the index n minus 1. I assume that this is already satisfied for the n minus 1. So if you wish, you can call this formula star with the n, and this will be a kind of determining equation for the gamma n. But by induction, I know that all such equations for the smaller n are already satisfied. So here in this computation, when I write this thing, I was using star n minus 1 formula. Okay, so I have 2 terms. So the third term is d prime n minus 1, f prime n minus 1, lambda n. So it has to be an easy check, because I'm essentially just get rid of one of the terms, since d squared is 0, and the other 4 terms supposed to be exactly the same. I'm just rewriting the other 4 terms. And I hope that I don't introduce any mistakes while I do this. So I want to show that this is 0. Well, if I want to do this, I kind of need to commute these lambdas, d's, and f's. And for this, the following is useful. Since the d squared is 0, I have the following formula: dn with the index n minus 1, lambda n minus 1, dn minus 1 double prime, composition with the next differential. So this is 0. But this gives me the formula, so this is equivalent, that the dn minus 1 prime lambda n plus lambda n minus 1 dn double prime is 0. Again, this is just the 0 that corresponds to this position in the matrix, because all other components are 0 by very simple observations. For example, d prime square is 0, d double prime square is 0. So since on the diagonal there is nothing. So now, with this commutation relation, I can, for example, take the first term, f n minus 2 prime, lambda n minus 1, dn double prime. Well, first of all, this is minus fn minus 2 prime, d prime n minus 1, lambda n. So I commuted the second and the third terms using the formula that I just derived. And then I can commute the first two terms. It will be minus dn minus 1 with the prime, fn minus 1 with the prime, lambda n. Okay, so now I can see that I can cancel first term with the third term. And then do essentially the same computation for the second term, and I see that I can cancel it with the fourth term. So this thing is 0.
Я не понимаю, откуда появились расчеты направо и слева, потому что если вы говорите, что это просто понижение степени звездочки, то там не должно быть f-2, там только f-1 должно быть, нет? Потому что в звездочке собой по себе только f-1, ну, с разными штуками.
Well, maybe that is because I have a, I have a problem here. This is minus 1. Well, let's check this star with the n. This is just you take product of this and this, right? And I think it's correct. Then I have a common minus and take the product of this, and you can see that indeed I have n minus 1. And for the signs, I think everything is fine, at least in this formula.
Ну, просто проблема в том, что тогда получается, что на другой, если перенести в другую сторону, там должно быть 2 плюса, а 1 минус. А у вас в скобке почему-то 2 минуса, а 1 плюс.
Here? Okay, so let's see. When I do this computation, so this will be this. Now this term is this term. Now this term is this term. So it has to be with the plus, right? Yeah, and the last term is with the minus. Well, actually, if we fix the sign here, but the next step is to take this composition with the d, and this is still 0, so it doesn't affect the rest of the computation, actually. But thank you, I have a mistake in my notes, I need to fix this. Yeah, so do you agree that this composition is 0? Because, well, this is just the same 4 terms, right? And then the last computation was, I noticed that the first term is equal to the minus third term by commuting this twice. So first I take these two things, I commute them, they get the additional minus because I have this commutation relation, and then I keep this thing and commute this thing, and this commute without any sign. So I'll get this thing, and now this is precisely the third term up to a sign. And the same computation, I don't want to do this, but just two commutations give you that this term is the same as this term, again with the minus sign. So indeed, this composition is 0. So this composition is 0. Now let's draw a diagram. I have Pn double prime. This is mapped to the kernel of the Dn minus 1 prime. This is embedded into the Qn minus 1. So this is map Gn. This is Qn prime. Okay, so let's look at this diagram. Well, this is the map Gn. So the way it is defined, it will be a map like this. Now, since the composition with the differential is 0, actually this is in the kernel of the differential. Right? I can embed the kernel of the differential here, and using this exactness, I can as well say that there is an epimorphism from the next step in the resolution to the kernel. Now, I use that this is projective, hence there is a lift of this map, and this lift is exactly gamma n. That's exactly what I want, because if I take the composition of the gamma n, the differential, well, I'll get this map, which is in fact this map. So I solved that equation for the gamma n. End of the proof. Okay, maybe any questions before I erase part of the proof?
Я не понимаю, что с чем сократилось, почему. Вот наверху на левой доске.
Well, this with this.
Почему?
Well, I start with the first term. This is the first term. Well, first of all, I commute, so I keep this thing, and I commute this, the second and the third factors in this formula, using this formula. So I get minus this thing. And now I commute first and the second, and they just commute without any sign. So if I do this, and of course I need to shift the index, I'll get this. But that's exactly the third term in this formula. With them. Exactly the same computation. Take one, here do the commutation twice, you get the last term. Okay, so next proposition. Sometimes this is called the dimension shifting or degree shifting. Now this is the following statement. Suppose I have the following exact sequence. So I have some km plus 1 that is mapped to the pm, p0, so exact PIs are projective. So in other words, what you see here, you take an object, you try to compute the complete projective resolution, but on the m's position, you stop doing this and just take the kernel of the differential. And this km plus 1 will be m plus y syzygy, m plus 1 syzygy of the object A. So then with this notation, I have the following formulas. So left to right functor LIF on object A is isomorphic to the left to right functor Li minus m minus 1 on the syzygy with the index m plus 1. And this is for any I which is at least m plus 2. So kind of replacing objects by syzygy, you can
Извините, можете вернуться. Окей, мы получили какой-то ноль, и что?
And then we use this diagram. So this is the map.
Okay.
So the composition of this map with the differential is 0. So it means that actually this is not the map to this module, but actually the map to the kernel of the differential. So in fact, this map is this map composed with the embedding. But now, using the exactness, this kernel can be covered by the Qn prime. Now, since this is projective, there is a lift of this map here. And this lift is precisely gamma n.
Почему это именно нужно gamma n?
Oh, because if you take gamma n, apply the differential, well, you get this thing, you get precisely Gn. Well, this is still Gn up to this embedding. So we solve this equation that I called equation equivalent to the star with an n. Found this gamma n. Yeah, so this is the first statement about the derived functors, and the second statement is that we have the following short exact sequence. Derived functor with the index m plus 1 on A is canonically mapped to the F applied to the syzygy with the index m plus 1, and this is mapped to the F applied to the PM. Okay, proof. Well, we have the following short exact sequences. Starting with K0 being equal to A. And this is just more or less definitions of the syzygy. You can always separate any resolution in such short exact sequences. Now from this, using that P is projective, I can conclude that the Ln F on the Ki is isomorphic to the Ln minus 1 Ki plus 1. And this is true for any n which is at least 2. Well, there's F missing in the formula. And this is precisely the long exact sequence that we just proved. This is the connecting homomorphism in the long exact sequence, because on the before this term and after this term I'll get zeros, because this will be the derived functor applied to a projective object, so it's automatically 0. Well, yeah, so, and of course from this formula we immediately get the first result of the proposition just by doing, so if I start with LIF applied to A, this is the same as Li minus 1F applied to the K1, and I continue doing this M, well, several times, M plus 1 times I guess. Li minus M minus 1 K M plus 1. Okay, for the second part, I look at the following diagram. So I have Pm plus 1 mapped to the Pm minus 1. So I kind of continue doing this projective resolution, or in the statement I stopped at the Km plus 1, but I can continue doing this, choosing this projective module and the next projective module. Of course, I assume that whenever I talk about the derived functors, left derived functors, I assume that they have enough projectives, otherwise they're just not defined. So this I can continue doing. Now, of course, I can splice these two resolutions together, and then I'll get just a projective resolution for the A. So then I can say that there is a differential with the index m plus 1, and this will be mapped to the Pm. Here, this will again Pm, and now this is just identity, and this is just the embedding. Okay, to this diagram, I want to apply functor f. So, at the moment, trying to prove this second formula. This we already done. This is here. So, but this I'm trying to prove right now. So I take this diagram and apply functor f to this diagram. So get f applied to the object Pm plus 2. This is f applied to the object Pm plus 1. F applied to the Km plus 1. Oh, I'm using that f as right exact. So here this will be f applied to the differential and end up in the f of the Pm, which is the same as the f of the Pm, and this is f of the embedding I. Okay. So of course, since these two objects are the same, I can as well just add 0 here and think that I kind of have this short exact sequence, trivial one, which just an isomorphism here. And then I want to apply the snake lemma to this diagram. So of course the kernel of the first map is very easy to understand. This is just f of the Pm plus 2. Now here I have some kernel, so let me just call this kernel of the f applied to the Dm plus 1. And finally I have kernel of the f of the embedding. Now, of course, then I'll get 0, clearly, because in this case the kernel is 0. Okay. So now, what I can say by looking at this exact sequence, this exact sequence and this exact sequence. Well, I can see that if I take this kernel, take the quotient by the image of this map, right? This will be exactly this kernel. But what's the quotient of this thing by the image of this? Yeah, by definition, this will be precisely the homology at the position m plus 1. This will be kernel modulo the image. So you'll see that this thing is just this quotient that is mapped, well, actually this quotient isomorphic to this kernel, well, and essentially just again splice two short exact sequences together and write the exactness here as this exact sequence. Okay. Okay, definition. Again, as usually it goes without saying that you have a dual version for injective resolutions and causes edges. So in definition, again, I have two parts. So an acyclic object, so an object, say Q, is called F acyclic. So by F I assume that F is the right exact. So that's the right exact functor between two abelian categories, well, modules for what we care. Okay, so if object is called F acyclic, if when you apply the derived functors to this object, you'll get 0, and that is true for any I positive. And 2, an F acyclic resolution of some A is left resolution Q with the bullet such that all the QIs are F acyclic. Well, for example, for any functor f, a projective object is F acyclic. The point is that if you're interested in just say one specific functor, you can find more objects, or you can use more resolutions than just projective resolutions. For example, we're going to see, I hope today, that for the torus we can, by definition we were using projective resolutions, but in fact we can use flat resolutions. So that will be one of the applications of this definition. And why this definition is interesting in general? Well, because we have the following proposition. If we have Q and F acyclic resolution, then we can use this resolution to compute derived functors. So then the left derived functor on object A is the same thing as the homology of the complex that I obtained by applying functor f to the resolution. Okay, proof is essentially based on the same ideas that the previous proposition. For this acyclic resolution, again, I can form short exact sequences like this. Well, by a little abuse of notation, we can still call this syzygies, but no, it's kind of syzygies with the non-standard resolution. Well, what we can say then as before, the nth left-right functor of f applied to the ki is isomorphic to the ln minus 1 f on the ki plus 1. And this is again from the long exact sequence for this short exact sequence, using the fact that all the derived functors starting with L1 are 0 on Q. So then, again, using the same argument as in the previous proposition, if I want to compute the left derived functor with the index n on A, I can as well just compute the first derived functor, but on the kn minus 1. So kind of can reduce computations for any derived functor to the first derived functor. So if I can show that for the first derived functor I have this result for any object, then I'm done. For this, well, essentially I'm kind of repeating this argument with the snake lemma, but for me personally I find it more useful just to repeat this argument. It's easier to follow and understand what I'm doing here. So essentially the same diagram, but for the acyclic resolution. And to this diagram I want to apply functor f. So let me just write it here. F of the Q2, f of the Q1, so then I'll have f Q0, f Q0, f of the embedding, f of K1. Again, I'm adding additional zeros to use the snake lemma. So here the first kernel is f of K2. This is 2, yes. So now here, though, this is still the differential in the resolution Q. So let me call this D, maybe D1. So then this will be f of D1. This will be some kernel of the f of D1. Okay. Now, the essential part, of course I'll get exactness here. So the essential part, what I need to put there as the question mark. Well, first of all, if I apply the same logic as before, this will be this kernel modulo the image of this thing. But this will be precisely, by definition, the first homology. Right? So this will be this thing when n is equal to 1. So on one hand, this question mark is h1 of the f applied to q. Okay. But what if we look at this, the vertical part of the diagram? So from the vertical part, what we can say about this question mark? This is the kernel of this map. Yeah, this is precisely L1. So this is, let me write this, L1 F applied to A. And why this is L1? Yeah, I guess you can say this, but I prefer doing this directly. Well, what would be the next map here? This will be the f. Well, we have a short exact sequence, 0, q1, q0, sorry, k1, q0, a, right? And if for this short exact sequence I apply factor f, then kind of I'll get, by the right exactness, I'll get f of a, f of q0, f of k1, and then there will be some kernel. And the kernel is exactly this thing. And this is the kernel of this map. Well, because on the next step, this will be L1 of the q0, and we assume that q0 is f acyclic, so it's 0. Let me just maybe... No. No. Let me just draw additional formula, additional long exact sequence. So this will be L1f of A. This will map to the f, k1, f, k0, fa, and then 0. I claim to have this 4-term exact sequence. Well, because I have this long exact sequence in general, right? So the next... No, the long exact sequence that we just proved in the beginning of today's lecture, you take any short exact sequence. This is a short exact sequence. And I apply a functor, and I get the long exact sequence for the derived functors. So then, why I can write 0 here? Well, that is because I'm supposed to write L1f of q0, but that's 0, because q0 is acyclic. And the diagram, vertical part of the diagram here is kind of take this diagram and rotate this. That's what you get. Okay. So we computed this question mark in 2 ways, and we see that this is first homology and the first derived functor on one hand and on the other hand. Hence, can we just finish this computation easily? So ln f of a, well, this is L1 f applied to the syzygy with the index n minus 1. And we know that this is h1 of the f applied to the complex with the qn minus 1, kn minus 1. Right? This is what we already proved. But now I can rewrite this computation, the last computation, as the homology at the position n of the original complex. Right? For this kind of shifted and truncated complex, this will be first position. This will be exactly as the nth position in the original complex. And hence these two things are isomorphic. Okay. So I want to actually start new section. This thing? Well, this we proved before. I already have this identity, and this follows by looking at these short exact sequences and applying the long exact sequence for these short exact sequences, which give me this formula. Because again, I'm using acyclicity. You can imagine that in the long exact sequence, I'll have ln on the qi here and ln minus 1 of the qi, but they are both 0. That's more or less by just looking at the complex. You look at this complex, you're trying to understand the homology at the position 1, right? And then you look at this complex and you realize that the homology at the position n is precisely the same quotient. Yeah, so I have, I think, maybe something like 10 minutes, maybe even less than 10 minutes, right? But I still want to start this new section, and I want to prove one theorem, state another theorem with essentially the same proof. And I think it's interesting and useful to know. So the theorem, sometimes this is called a theorem about balancing balancing Tor. So here is the statement. So let P be a projective resolution of right module A, and Q is a projective resolution of left module B. So then I have the following. The Tor is the index n between modules A and B. So A is, of course, right module, B is the left module. So the way it was defined, it was homology at the position n. I take the resolution of A, take a tensor product with B, and compute the corresponding homology. That was the definition, so there is no statement here yet. I claim that actually this is isomorphic to the homology at the position n. I keep A, but now I replace B with the resolution. So kind of this definition of a Tor is symmetric. I defined in one way that I resolve the first argument, but you can keep the first argument and resolve the second argument. And let's temporarily, it will be useful for the formulation of the proof, call this second homology Tor with a little t. So this thing is just definition of the Tor with a little t. So the claim is that Tor with a large t and Tor with a little t is the same thing. So the definition kind of balanced. Okay, so proof. Well, first of all, I introduce syzygy for the both of the resolutions. Ki mapped to the pi mapped to the ki minus 1. This is one short exact sequence. Of course, I can assume that k0 is just A. And for the second resolution, I have 0, vj mapped to the qj mapped to the vj minus 1, 0. And as before, v0 is B. In the first formula, the index is I. In the second formula, the index is J. So essentially, this whole proof is based on looking at one diagram, which is just tensor product of these two short exact sequences. So let's take a tensor product, and this is what we get. So I have Ki tensor product with Vj. So this is mapped to the Ki tensor product with the Qj. Ki tensor product with Vj minus 1, so this is 0. So the second row is pi j So all the maps in this diagram are supposed to be easily identified as just a tensor product of maps. Yeah, and I've done my best to distinguish I and J. Okay, so this is what you get. Well, of course, you get zeros on the right because the tensor product is exact on the right. Well, actually, you have a little bit more. Well, of course, on the bottom you also have zeros. You can notice that, for example, here the first row, well, this is just tensor product with ki of the second short exact sequence. So this is tensor product with the pi of the second short exact sequence and the tensor product with the ki minus 1. And the same is true for the columns. If you, for example, look at the first column, you take the first short exact sequence, take a tensor product with the vj, and etc. So these zeros will get automatically, but then also we'll get 0 here, right? Well, that is because we assume that Q is a projective left module. And we also get additional 0 here, again, because we assume that Pi is projective. And in the other positions we won't get zeros, but let me give some names to these things. So this thing I'm going to call Z. This is the kernel of the map B. Now this is Y, and the embedding will be iota sub Y. And this is the kernel of the map A. Now this is called X, and this is the kernel of the map F. And the embedding map is the iota sub X. So this will be a map here, and this will be a map here. So I'm also claiming that these two squares are commutative, and this is because, well, essentially by the neutrality that we proved in the beginning of today's lecture. So finally, this last kernel I'm going to call W, so this map is H, so W is the kernel of H. Okay. This is the diagram, and from this diagram I claim that I can see the proof of the theorem. Okay. Well, first of all, let's identify what's the W. I claim that the Tor 1 k with the index I minus 1, v with the index j minus 1 is isomorphic to the W. Okay. Well, for this, I guess we just need to look at this column and imagine what would be the corresponding long exact sequence. And you'll see that the kernel of this map H is precisely the Tor 1. Now I can do the same now for Z and this row, exact row. So two claims here. Well, first of all, W is isomorphic to Z. Let's postpone this for a minute. And the second claim that the Z is a Tor with a little t for the Ki minus 1, Vj minus 1. Well, the second isomorphism is more or less the same as the first isomorphism. Just look at the corresponding long exact sequence. Now, why W is isomorphic to the Z? Well, I claim that this is an application of the snake lemma. We just need to kind of recognize what we want to use for the snake lemma in this situation. Yeah, so let's look. Have colors. So for the snake lemma, we'll look at this part. And apply snake lemma to this part of the diagram. Well, then these three things will be precisely co-kernels. Now for the kernels, I know that I have some kernel here, here gets 0. So then I can say that this W is actually the kernel of this map. But the kernel of this map is Z. Hence W is isomorphic to Z. Well, look at the diagram. I choose a diagram in the red and I apply it for this part of the diagram, the snake lemma. Yeah, so I take this diagram, take these three maps, compute kernels, This will be 3 objects here. Compute co-kernels. This will be 3 objects here. And there is a connecting map from the kernel to the co-kernel. But now, of course, this kernel is 0. So here I get just this kernel, and the claim is that this kernel is precisely the kernel of this map. If I have an exact sequence with 4 terms, kernel and 3 co-kernels, then W has to be isomorphic to Z. Okay. This gives me the first relation between Tor1 and little Tor1. Now, Y, what's Y? Well, this is by definition, where is Y? Kernel of the map A. Or as well, image of the iota sub Y. Well, I claim that the image of the iota sub Y is contained in the kernel of F. Right? So the image of this map is in the kernel of F. Well, that is because this composition is 0, hence this composition is 0. So if the composition of these 2 maps is 0, then the image of this is contained in the kernel of the second map. So this is contained in the kernel of F. Well, the kernel of F is the same thing as the image of the iota sub X, which is, of course, as well can be identified with X. So both these things. Okay, now kernel of the iota sub X is contained in the kernel of A. The same reasoning. I look at this commutative square, so this composition is 0, hence the image of iota sub X is in the kernel of A. But I started with the kernel of A and I finished with the kernel of A. And I had X in the middle. So from this computation, X is isomorphic to Y. But what's X? This is Tor1 between Ki minus 1, V with the index J, isomorphic to X. This is isomorphic to Y, and Y is isomorphic to the little Tor Ki Vj minus 1 by the same reasoning as before. And finally, I can actually combine this with my first computation and say that this is also isomorphic to the Tor1 Ki Vj minus 1. Right? Because I know that I can replace Tor1 with the large t and with the little t if I keep the same arguments. Now, the last computation that gives me the proof of this theorem. Tor with the index n between objects A and B, I can compute as a Tor1 with the syzygy kn minus 1 b. That's a proposition, well, one before the previous one. So this is isomorphic if I use the formula that I just proved on the previous line to the Tor 1 a v n minus 1. And finally, this is the same thing as the little Tor 1 for a and vn minus 1. And now proposition 1 before the previous one, this is, but for the functor little Tor n a and b. End of the proof. Okay. Any questions before I erase this theorem?
Вопрос, чем, собственно, отличается, то есть почему нельзя все то же самое сразу было сделать А и Б?
What do you mean, the same thing? The point is that I'm going from the n to some syzygy, then I'm using what I proved before, that I kind of can move this syzygy from the first argument to the second argument. Then I can identify with another derived functor in the second argument, and then I use what I know about the derived functors in general. So I don't think that you can avoid this computation and don't use syzygy. Oh, but anyway, so from practical point of view, we can say that it doesn't matter which argument we derive, the first or the second. And this also gives us immediate application for example, if I want to compute tor n, say between A and B, well, I claim that this is 0 for n positive if B is flat.
Что это значит?
What part? B is flat? Well, flat as a module, meaning that the tensor product with this module is exact. Well, if you, for example, don't know this theorem that we just proved, actually you need to prove this separately. It's not immediately clear because in my kind of definition that I gave last week, I need to take the resolution of A and do some computation, then something of this kind maybe, and then realize that this is actually 0. But if I know this theorem, I know that I can as well kind of derive this, do the other thing. I can resolve the first argument, but if I resolve the first argument and tensor product with B is just an exact functor, and exact functor doesn't give me any new homology, so homology will be trivial for n greater than 0. So in particular, we can see that for computations of tor n between A and B, we can use flat resolutions. Well, this immediately follows from this observation on the flat modules, the direct functors are 0, and the proposition that we proved at the end of the previous section, that we can use acyclic objects to construct resolutions. Okay, and finally, this theorem that I just proved about balancing tor has an analog, so let me call this theorem star, and this is balancing X. It's kind of more or less the same statement. So let P be a projective resolution of A. So of left module A, and suppose that the module B has injective resolution. So injective resolution of the left module B. So then as before, if I just remind you the definition of the X that I was using, so between A and B, two left modules, I was saying that I need to do the following. I take the home from the A that I apply to the injective resolution and then compute the homology. That was our definition of the Xn. But you can do the same thing. You compute the homology of the home where you resolve the first argument, so apply the resolution and keep the second argument. So let's call this X with a little e. Again, doesn't depend which argument you're resolving, but you need to notice that the second argument is resolved with an injective object, and the first argument is in injective resolution, and the first argument is resolved with the projective. That is, the reason for this is because the home is contravariant functor, so it's actually from the opposite category, and in the opposite category this projective resolution becomes an injective resolution. Да.
Потому что это двойственная крутой?
Да. Oh, the proof is, I'm not going to give you proof because the proof is more or less the same. You take the two resolutions, short exact sequences for these messages, and take homes and use more or less the same arguments. A little bit more complicated for this part, because instead of kernels you're not going to need to use co-kernels, but more